Hello, everyone. Thanks for joining today. My name is Jordi Sulen. I'm doing global business development for our electromagnetic and electronic solutions. It is a pleasure to be here to talk about how we are helping our customers to solve design and analysis challenges related to electronic systems in connected vehicles. This is the outline we have for today. At the beginning, we would like to talk a bit about Altair and the connected car market. Afterwards, we would like to talk about our solution for connected vehicles, where we have included a few nice use cases from major automotive companies, including OEMs and tiers. And at the end, we would like to talk about V2X in the context of ADAS. As stated by our founder and CEO, Jim Scapa, our vision is to leverage data analytics, simulation, and high-performance computing to help our customers transform the way they are making decisions. And Altair is a public company listed on the NASDAQ. We have more than 11,000 customers using our strong portfolio with more than 150 products. Revenue last year was around 460 million. We are really a global organization with more than 3,000 employees. We are headquartered in Troy, Michigan. The company was founded 35 years ago. And we are spread around 25 countries with 86 offices. If we look at the portfolio, we talk about design modeling and visualization, multiphysics simulation, data analytics, our platform for IoT, high performance computing, and through the Altair Partner Alliance and our licensing system, our customers have access to also third-party applications. In terms of industries and verticals, we are really present in most of the major verticals where, of course, automotive is a very important one. And where all these customers are leveraging our unique licensing system, where basically this is what we call the Altair units. There is a pool of units, and the number of units that you draw depend on the products you are using, where you are running the simulations, and also the number of simultaneous jobs you are using. And it's really scalable and flexible and much more cost effective than other licensing mechanisms in the market, where if you want to use an additional tool or module, you need to pay extra. Now, if we talk about the connected car market, here you can see some statistics from Statista, where you can see in terms of the market size in $1 billion, the big jump from this year to 2025, where we are seeing that the market will grow with a factor of 3 in the next 5 years. And we're also in connection with connected vehicles, we need to talk about 5G and autonomous cars, where we see the automotive and telecom industries working together. And a nice case of this is what you can see with the 5G Automotive Association, where basically they are working on end-to-end solutions for future mobility and transportation. And they are working on some of the most important use cases. And later today, we will explain how to address some of these use cases using simulation. Now, with respect to our solution for connected and electronic system design, we're talking about this, where at the board level, we have technology basically for PCB design review, analysis, verification, and manufacturing. Then when we go to system level, we have our electromagnetic solutions for connectivity, EMC, and radar. For multiphysics simulation, we cover, among others, electronics, cooling, electric drive systems. And when we talk about chip design, we have the fastest HPC job scheduler. And last but not least, we have a visual environment for firmware development. And today, we are going to talk mainly about our connectivity solutions with our electromagnetic simulation capabilities. When we talk about vehicle connectivity technologies, we are basically talking about all the technologies available from cellular, 3G, 4G, 5G, Wi-Fi, Bluetooth, satellite navigation and communications. And this, for example, includes GPS and Sirius XM, vehicle to X, remote keyless entry systems, radio broadcasting, and others. And in particular, with respect to V2X, we basically have the SRC, which is not relying on cellular infrastructure and being important for road safety and traffic efficiency. And also we talk about CV2X, which relies on cellular infrastructure and where we see an evolution towards 5G, where the use cases related to safety are important and also in connection with autonomous driving. And this is a video we would like to show you where we explain our offering and solutions for connected vehicles. I hope you have enjoyed the video, and now we would like to go a bit more into the details, where basically with our solution for the different technologies, we are talking first of all about the design, placement, and optimization of antennas in the vehicle. Then we talk about simulating the drive tests that are used to validate installed antenna performance, and also the drive testing for connectivity, including range, data rates, which are important for vehicle-to-vehicle and vehicle-to-X communications. And in terms of the workflow, here basically we start with Hypermesh to clean up and mesh the model, including automation. Then in FECO, is where basically we design the antennas and optimize their placement. And after we have WinProp, we're using the antenna simulated in FECO and simulating the real environment. We are analyzing the drive test and the connectivity aspects. This is an example from Daimler in Germany in this car related to remote keyless entry antennas. Basically on the left, you can see the different antennas in the key fob, but now I would like to ask you to focus on the images you can see on the right, because there you can see how Daimler is analyzing possible different positions for the antennas in the rear screen, spoiler, and side mirror. And by doing simulation, what they are doing is they are analyzing the near field patterns for the different positions, and they are comparing these patterns, especially looking at the shape and the nulls, because depending on the direction, it may happen that the communication between the key fob and the car is not possible. And in this case, this may mean that the user may not be able to lock or unlock the car from some specific direction, something that obviously they want to avoid. And if we move to virtual drive testing, and this is another case, in this case from an automotive supplier, Catherine, now Continental, where basically they are doing multiple drive tests to validate the installed antenna performance. This is an example where they for an LTE antenna using MIMO. This is the reason why in the photo you can see two antennas. And at the bottom, you can see an image of the area where the blue circle is the base station. And in red, you have the test track, while what they are doing is they are driving the car along the route. And then while they are driving, they are measuring the received signal by the antenna in the car. And this is something that they are basically doing measurements, but this type of measurements are costly and very time consuming, and they are now moving to simulating all these drive tests. And this is a comparison of receive power against distance, where they compared their measurements with the simulated results using our technology, where you can see there is a nice agreement between them. And now, if we talk about vehicle to vehicle, and this is also from another automotive supplier in Europe, where basically they wanted to analyze two scenarios. The first one is they wanted to simulate and ensure the range of the communication between two vehicles is bigger than 500 meters. Where here in this image, you get the red car is static and the blue car is moving. And the second scenario they wanted to analyze is a case where there is no line of sight between the two cars. And you will see in a moment why this is also important. If we look at the results for the line of sight scenario, basically in this image, and if you look at the legend, this is received power by the blue car while it is moving along the track. And a bit more in detail, you can see in this graph where the black line represents the sensitivity of the receiver. There is no issue in achieving the desired range, even when you are using different types of antennas in the vehicle. If we now look at the other scenario, this is the non-line of sight one. The situation is a bit different because, as you can see in the image, the two cars are not seeing each other all the time. And then there are some areas which are here shown in green, where there is no communication between the vehicles, something you can more easily see here when looking at the areas below the sensitivity level. And in these areas, there is no communication. And this is something which needs to be carefully analyzed because, for example, in one of the use cases that I was showing before, you can have two cars approaching an intersection and you want to be able to have communication between the two of them before approaching the intersection. It's not only about received signal strength, but also it's important to have the possibility to analyze other parameters. And this is, for example, a comparison of the data rate against distance when you compare the DSRC against the LTE technology to analyze and compare the benefits of using different technologies when doing vehicle-to-vehicle communications. To finalize the presentation, we'd like to talk about V2X and the relation to ADAS. And in fact, V2X has become an important part of ADAS systems to communicate the cars, and as I have shown today. And also, we are touching on, and we have solutions for radars, for ultrasonic, and for LiDAR, where for LiDAR, we basically, our customers, they can leverage the Trace Pro application. This is a third-party application available with our licensing system through the Altair Partner Alliance. And with respect to radar, we basically talk about 3 levels of integration for the sensors. The first one is what we call the integration scenario analysis and scoring. And here we are looking, for example, in the case of integrating an antenna in the bumper, we are looking at the properties and the characteristics of the bumper in terms of layers and paintings. The second level of integration is related, in this case, to the simulation of the antenna and the integration of the antenna in the bumper. And where on this graph on the right, what we do is we compare the radiation patterns of the antenna in the bumper. And here you can see a comparison between simulations and measurements. And the third level of integration is related to virtual test drives, where this is a case where we have many customers working on this. You have a car going through a bridge, and the car is slowing down because it's detecting some false object. And this is why here we talk about a false detection. And the reason for this is basically here, where on the right, you can see that the antenna pattern has a side lobe which is higher than expected. And this is because in the integration phase, it was not properly addressed the fact that there is a badge in front of the antenna. And this badge is responsible for the increase of the level of the side lobe, which is then responsible for this false detection. And that's all what we have for today. Thanks for watching, and we would be happy to continue this discussion with you to see how we could help you.